Okay, so this is Wireless Communications Lab, lecture number 4. So I'm Robert Heath at the University of Texas at Austin. So for this lecture here, today we're going to complete some of the work on stochastic processes that we didn't finish in the previous lecture. And then we're going to transition to Fourier transforms. You have seen Fourier transforms in many of your previous classes, and so we're just going to focus on defining and computing two of the transforms that we use a lot in the class, the continuous and discrete time Fourier transforms. We'll actually leave the discrete Fourier transform for a little bit later in the course. And then the second thing that we're going to do is look at this basic property of communications, which is that communications systems send band-limited signals. And that's going to form the foundation between the connection between digital communication and signal processing. And based on that connection, we'll review the sampling theorem, talk about how to calculate the Nyquist sampling frequency, the sampling rate, how to sample the signal, how to reconstruct the signal, and demonstrate aliasing. So these are all things that you should be able to do by the end of the lecture, and ideally you've been able to do them at the beginning of the lecture as well. With that, let's get started here on just completing the, let's see, previous lectures material on random processes here. So let's see. All right. Okay, so last time in the lecture, we talked about wide-sense stationary random processes. And so we showed that, this was, we have a random process, a sequence x of n, that satisfies these two important properties here, satisfies that the mean of x of n is a constant, and then the correlation function, or equivalently the correlation, and I'll write this differently here, is a function of the difference n2 minus n1. And so what we'll see is that for wide-sense stationary random processes, they will have a correlation function that looks like this here. It's a function of only one number. And then this example I was using last time here, so if you, just for an example, suppose that you computed x of n1 comma n2, and you found that that was equal to n2 minus n1 squared, let's say. Then you would say, aha, this is only a function of the difference. Therefore, I could write equivalently cxx in the following form, like this here. So essentially that's what it means here, is that when you go through the tedious calculation of the cxx of n1 and n2, you'll find it's only a function of the difference, and therefore it can be written with a single variable here. So that's basically what wide-sense stationarity means. Now, one of the problems that we encounter being, actual engineers doing stuff in the lab here is that, this concept applies to the theoretical calculations here, given the probability distribution function to compute the mean and to compute the correlation. So in a lab, we don't have these probability distribution functions. In a lab, we have a realization. And so let me just illustrate that here. So the way that these expectations you can see work here is that, so let's say that this is a discrete time signal here. So this might be realization x1 of n. And this might be realization x2 of n. and so on here. So these are different realizations. And kind of intuitively, what I could do would be average, for example, all of these. So this could be 0, 1, and 2. And I could get an estimate of mx hat of 2, for example. Now the problem is that you need many realizations of this random process. And what we find is that, in the lab, in reality, we have only one realization. We want to transmit this file from point A to point B. So we have just that one file to deal with. We don't get to have a whole bunch of different ones. And so this is a problem here. So this is a way to estimate the expectation of x of 2 here. So a solution for this problem is what's called ergodicity. So ergodicity, like probability and stationarity, is itself like a very deep mathematical subject. Essentially, what it means is that if a random process is ergodic, so under ergodic assumptions, the time average or sample average converges to the expectation. And so essentially, with ergodicity, one could take just one realization, average, and get something that is approximately mx hat here. So instead of having to have multiple realizations of this sequence, we can have one realization of the sequence and use that one sequence to get a good estimate of the different sample moments here. And so there's different notions of ergodicity, ergodic in the mean, ergodic in the covariance, and so on here. But that's the main concept. So we're going to use one realization to estimate the moments. Now the connection to Whitesense stationary random processes is as follows here. So it turns out that Whitesense stationary random processes are usually ergodic. Now the exact conditions are given in the book. It comes from something that's called Slutsky's theorem. And so in that theorem, that will tell you the exact conditions. And it turns out essentially that there's a certain summability constraint imposed on the covariance function that in practical systems is satisfied. It's only, it's only in these kind of mathematical constructions that we see that these processes aren't. So for all practical purposes, the signals that we want to assume are Whitesense stationary in the lab, we can also treat them as being ergodic as well. And what this means is that we're going to look specifically at ergodic, second-order ergodicity. And so we're going to use these practical estimators. So I could say that mx, this is the expectation, is the result of taking a large number of samples and averaging them in time. So if we look here, this is just, I take more and more samples, I add them up, divide by n. And what we're saying is that if it's ergodic, this means that this is the sample average And this is what's called the ensemble average. And so the sample average converges to the ensemble average. And then this also gives us a practical way to estimate the mean. So we could say that, for example, mx hat, our estimate of the mean, will be 1 over n, sum from n equals 0 to n minus 1, x of n. And presumably, n would have to be reasonably big to get a good estimate. The rule of thumb is that you need about 1 order of magnitude per order you're estimating. So for a mean, n would be on the order of 10 as a rule of thumb here. Now we can also use the same concept to get I'll give you the correlation estimator here. So this is ergodic, the second order. Then for large numbers of samples, this estimator 1 over n minus k, sum from n equals 0 to n minus 1 minus k, x of n, x conjugate of n plus k. Let me think I had that right here. Yeah, n plus k works. Converges here. And so we can use rxx hat as 1 over n minus k, sum from n equals 0 to n minus 1 minus k, x of n, x star of n plus k as our estimator. And notice that this is only going to be good for n from 0 to n minus 1. Now we'll see, we talked a little bit about this in 351M, but essentially there's other ways to derive, some better estimators here. So that's something that we won't cover in the class here. But why I wanted to mention the ergodicity is that even though a lot of the times in class we're talking about using the ensemble averages, I'm going to use mx and rxx of k, you can think in your mind what I really mean is mx hat and rxx of hat here. And this is important because if you want to estimate those things in the lab, you can implement these functions here in LabVIEW or C or MathScript and derive an estimator. So if we derive a function of mx and rx, you can use the time average in place of that. So that's essentially the concept here. So any questions about this ergodicity before we go on? Okay, so the final thing that I want to mention in the probability random processes is just the IID Gaussian random process, because this is the model that we'll use for our noise. So this is the model for additive white Gaussian noise, or AWGN. And so essentially this is a random process where which is basically IID. And we're saying that not only do we know that it's IID, so it's white stationary, but we also know the distribution of those elements here. And it's Gaussian here. So if it's real, then I would say that x of n has some distribution, for example, like this, where this is the Gaussian distribution, fx, let's say z is equal to 1 over square root of 2 pi sigma squared e to the minus z minus m squared over 2 sigma squared here. And then if it's imaginary, if it's complex, I should say, we treat this random process as something special. It's called circularly symmetric complex Gaussian. And this is a special kind of a complex random process. So we say that x of n is distributed as n of, and I often put the c there, but since we usually just deal with this one, I might omit the c. So we get n of m comma sigma squared, and what this means is that the real part of the expectation of x of n, I don't know what that sound was, is going to be equal to the real part of m. The imaginary part of the expectation is equal to the imaginary part of m. And then the, let's see here, the real and imaginary parts are independent with the same variance here. And so the circular symmetric is this independence between the real and imaginary. You could actually have them being correlated, and then that would give you a more general complex Gaussian random process, but that doesn't model what we see in communication systems. Now, it turns out that with all of these assumptions, what you can do is you can actually give the distribution function in this form here, where this is complex. I'm sorry, let me make that a z here. So normally, a distribution function for a complex random variable, you have to write using the real and imaginary. But it turns out for this very special case, you can write this as 1 over pi sigma squared e to the minus z minus m absolute value divided by sigma squared. And so this result here we're going to use several times in the course. The fact that this is the distribution function for a complex Gaussian random variable. And so an IID Gaussian random process is independent, identically distributed. Every sample has mean m, variance sigma squared Gaussian distribution. So that's all it means here. And so then we might write that, c xx of n1 comma n2 is going to be equal to sigma squared delta of n2 minus n1. That's one of the implications of this here. And that delta comes from the IID property. All right, so that's all for the stochastic processes review. Any questions about these random, either what we've done right now or in the previous lecture on random processes? And this is a good area where we'll have some homework problems on this, but it's good to work through the examples yourself. It's good to try some of the homework problems that aren't even assigned, just to get a feeling for these calculations. So the main ones are, showing something is White-sense stationary, and sometimes that can be somewhat tricky. Okay, so now we're going to take a whirlwind tour of Fourier transforms. And so the things I want you to be able to do is I want you to be able to define the transforms, and hopefully you can do that already. I also want you to be able to compute the transforms. In particular, I want you to be able to compute them not using brute force, but using the tables and the properties. Because, really, we study Fourier transforms to derive intuition on systems. We don't study Fourier transforms to practice integrating and doing calculus again. So that's the main takeaway is I want you to be able to apply these using the theorems and the transforms. Okay, so let's see. So 4 here. Okay, so in the class we deal with continuous and discrete time signals because, we're going to have those sequences of symbols and we're going to have that continuous time signal that we send. And we're going to have to process that signal too. So we need both continuous and discrete time Fourier transforms. So I'll just go through these real quick here. So the continuous time Fourier transform this is the one, so we'll use this a bit. This we're going to abbreviate as CT-FT. And then essentially this says that, well-behaved function x of t has a Fourier transform x of f, and they're related as follows here. So this well-behaved, I'm not going into the details of this, but remember that if you can't integrate, then the Fourier transform may not exist, or it may exist using a generalized function like the Dirac delta function here. So the analysis equation, this is going to be x of f. This is the sum over t, x of t, e to minus j, 2 pi ft dt. And then the synthesis equation is x of t integral over f, x of f, e to the j, 2 pi ft df here. So this is analysis. This is synthesis. And so for the transforms and their properties here, so I won't go through all of these here, but I'll refer you to, this is table 1 that's in the book here. So hopefully you're familiar with these here. But what we're going to do is we're going to have several problems where you're given some complicated function, like I'll tell you x of t and y of t, and give you some function of these, and you'll have to use these properties to determine, what the actual transform is. And a lot of these are important. I mean, like we're going to see this frequency shifting property come up again and again. We're going to see the modulation property come up again and again here. And you can see here that multiplying by complex exponential shifts the spectrum. Multiplying by a cosine shifts it and gives you mirror images. Multiplying by the sine shifts gives mirror images and an imaginary piece. And then the real, even, and odd. So some of these, because x of t is complex, might be less familiar, but we'll use these different properties in the class here. So I'll refer you to the textbook for that. I also refer you to the textbook for the notation and transforms of several common functions, like the Dirac delta I'm using as a delta of t, complex exponential, the unit step function, the sine function, the impulse train. And you can see this in the book here. So please take note of these common transform pairs. Okay, so that's the continuous time Fourier transform. Another transform that we will also use, mostly in connection to the continuous time Fourier transform, is the continuous time Fourier series. This is the CTFS. And I realized that, I used to, when I taught this course, this was familiar, but at some point we seem to have gotten rid of the Fourier series from the 313 curriculum for reasons I don't understand. So that's kind of weird. But anyways, the continuous time Fourier transform is going to look like as follows here. So suppose that we have a periodic signal x of t with period t, then it has a set of Fourier series coefficients such that, these coefficients x of n are the result of integrating that signal over one period. Any period will do. E to the minus j 2 pi over t n t dt. And then x of t is an infinite sum of these coefficients here. And so the way to think about this here is that effectively when you have a periodic signal, it has a discrete spectrum instead of a continuous spectrum like an aperiodic signal here. And these are the frequencies that are important. And so essentially, any periodic signal x of t can be written as a linear combination of complex sinusoids that all have period that is an integer multiple of n, essentially an integer multiple of 1 over t. So the fundamental frequency is 1 over t. So I should write that down here. Fundamental frequency, 1 over t, and so that's the property of periodic signals. Now, where we use this continuous time Fourier transform is that we use it to define the continuous time Fourier transform of a periodic signal. Because a periodic signal, if you try to take its continuous time Fourier transform, the integral just blows up because it's periodic, it's infinite energy. So what we do is we define this, and so we end up with x of f of x is equal to the sum over n, capital X of n, delta of f minus n over t. So this x of n here, that's our continuous time Fourier series coefficients. This is the fundamental period, and this is f, and all that infinity is captured over here in our good friend, the delta function. Delta function is what we always pull out to deal with these kind of weird cases where stuff doesn't converge, and it's one of the reasons why physicists don't like engineers is because of that delta function. Mathematicians too. And then the synthesis equation ends up being, let me think here. Yeah, it's just the same as the other one here. And so the spectrum of a periodic signal would look, we would write it something like this here, where this is f, these are the fundamental frequencies, and these values here, like this is, x of 2 over t, which is equal to the absolute value of x of n here, times delta of f minus something like that here. So anyways, that's the so-called comb spectrum. It was really funny. This morning I was packing, and I was realizing that I'm packing a comb for my trip. I just had this realization, why? What am I combing? So I took it out, and I saved myself a little bit of space here. It's great. It is. Well, it's actually one of these foldable brush combs, so I saved about, this much. I'm going away for a week, and I'm just carrying an extraordinarily small bag, so every square inch matters. All right, the last transform I want to mention is the discrete time Fourier transform. Okay. So this is discrete time Fourier transform. I guess I should spell it out again. Hopefully I don't need to do that here. So the discrete time Fourier transform, this is actually one that I want to mention because in this class I end up departing from the notation from 351M and 445S, and I use frequency in discrete hertz instead of in radians. And actually, having taught 351M now several times, I was sort of thinking of going back, but anyways, I'm stuck here. So for a well-behaved sequence, the discrete time Fourier transform is defined as, this x e to the j 2 pi f. So in a lot of the other classes that you've seen, this was e to the j omega. So I'm actually putting 2 pi f here. And otherwise, the stuff looks exactly the same. So sum from minus infinity to infinity, x of n, e to the minus j, 2 pi, f of n. And then the synthesis equations are given by x of n, integral from minus 1/2 to 1/2, x e to the j 2 pi f, e to the j 2 pi fn df. And so, we're not using radians, so this x e to the j 2 pi f is periodic in f with period 1. Right, so here we could integrate from 0 to 1, or we can integrate from 2 to 3, whatever. It's periodic with period 1. And then we measure f in, essentially is like frequency instead of radian. So we often look at f on minus 1/2 to 1/2. Now, the properties here, so this is also one that I've provided tables in the book. And I would suggest to go through these because most of them are the same, linearity shifting, the usual stuff. But, like when you come down here, there's a few properties. Let me see if I have any here. Multiplication, for example, where when you deal with radians, you get a 1 over pi, or a pi that just sticks in there for no good reason. And so the nice thing about working in Hertz is that little factor of pi doesn't show up. So that's just the one thing to take note of here. But otherwise, everything works exactly in the same way. Parsifals, for example, there's no pi in there. It's a sum in discrete time, integral in this continuous time. So be sure to go through those, and then be sure to check out here's another nice thing here. Cosine, and radians has a pi here. There's no pi here. So anyways, no pi in some special cases. All right, well, that's essentially what I wanted to say about transforms. Does anyone have any questions about that? Guess not. Again, the reason to go through this is that we will be using the transforms a lot in class, and then I will have you work different exercises on the homework to show that you know how to use the transforms. We need this because communication systems, a lot of times we have to think in the frequency domain. For example, we're going to have to create signals that achieve certain spectral masks, according to the FCC. Spectral mask is a property of a signal defined in the frequency domain. We're going to create modulated signals that have good frequency domain properties. So we need to understand how the frequency domain works. We're going to equalize signals in the frequency domain. So we have to understand how linear time invariant systems affect signals and how we can remove those effects. So the transforms they're good for intuition. They're also really good for debugging stuff. If something's not working right, what happened to the received spectrum? Is it shifted? Is it scaled? That can give you some clues about how your software is misconfigured or how your hardware is having problems. Okay, so that's, let's see, Fourier transforms here. So now we're going to take a slight detour to the tileapp.com. And sadly, I get no, no financial support for mentioning any of these companies. So let me go over here. I want to play this little video here. It's kind of corny, but
this is Tile. Tile helps you find things, anything. Stick it to your laptop and worry less. Attach it to your keys and never be late. Drop it in your purse and you're good to go. It works very simply. Finding things with Tile is easy. Through the Tile app on your phone, you can track distance to your lost item. The app shows you as you get closer. And Tile has other features too. You can log into your Tile account on anyone's smartphone to search for your items. And you can also activate a tile to ring so you can find it by sound. tile is affordable, and it's tiny. You can even securely share tiles with others using our cloud-based platform, which is great for families. No matter who used the car last, the keys can always be found. If your bike goes missing, you can mark it as a lost item. This puts all other tile apps on the lookout for your tile. If any tile user gets within range of your bike, their phone will discreetly and securely communicate with our cloud system, and you'll be sent a notification of your bike's whereabouts. Let Tile find the small things, so you can find the big ones.
Yeah, we'll stop it there here. Blah, blah, blah. Okay, all right. So anyways, I saw this here. You know, I got to it from a sundry website I was surfing on. I don't know how but it's something that we've talked about like a lot at UT, because another aspect of wireless is also location. We don't talk too much about this. They have some nice classes in the aerospace department and faculty that work on navigation and positioning. And this is sort of just another feature of wireless that's also really cool. And you can use the concepts from this class to do positioning and navigation as well. Anyone have comments on this? I mean, would you all use this?
I don't think it can be used for lost or bike, for example.
Indeed, yeah. Yeah, I also thought that one was a bit of a stretch. And also you need enough people with tiles around to pick it up, right? Because this is based on Bluetooth communication. So it's not using, so you have to be within some 150-foot proximity or less. So. Yeah, I mean, you can attach it, but, I mean.
Yeah, but to do that, you have to find a place where, like, somebody wouldn't see it or something.
Right.
If you're talking about your bicycle somewhere hidden.
Yeah, it's possible. There's a comment in the back. Yeah.
How do you keep it charged?
Oh, yeah, so that's interesting. It is, because of the way it's designed, the battery lasts for more than 1 year. And so you can only use it for 1 year, and then you have to get another one. So it's $20, and instead of having something where you get a new battery or whatever, you buy a new one every year. So that's kind of their alternative to the subscription model, and they have some justification for this that, it lets you get a better one every year and a longer lasting one, blah, blah, blah. That's the idea. And they say, it makes it waterproof, because you don't have to exchange the battery. And that's, from a communication point of view, is pretty cool, because it means it's very low power. And I don't know if it uses harvesting. Probably not. It's probably just a very, very efficient radio. So, I mean, for me, I have to say I tend to lose my keys more than I used to. So, maybe this is going to appeal to a slightly older crowd. Not you all who are, are invincible at this point.
She was like 15, though. She was like 15.
That girl in there? I think she was meant to be like 18, I think. Anyway, she had a hard time in high school, did a lot of things she shouldn't have, forgetful now. What can I say?
I like how she feels safe, but like, I'm only leaving my laptop here and just walk away because no one will steal it because there's a little piece of plastic on it.
Yeah.
The acting is
Yeah, having been to Spain, I understand that that's extraordinarily naive. In fact, you're just lucky if you're typing on it and you don't just look over here that someone steals it while you're like typing on it. Not to pick on Spain, but that is a country where this has happened, and I resonate with this because my bike was stolen in Spain. So I was really annoyed at that time. Like, yeah, why can't I track that? And anyways, exactly that kind of setting too. But it was really nice because it was stolen like 15 feet from the building where I was working in. So it's just like, seriously? I mean, ugh. So yeah, we'll see. Startup. Yeah, looks cool. It's got wireless.
Sorry, can it only communicate with other tiles, or is there other ways?
It seems to communicate with the phone, and then I think it somehow can network with other tiles. I'm not really sure if it uses like a multi-hop.
So we can't access them. Instead of let's say that there's not another tile within the vicinity, wouldn't be able to contact, I guess, via the internet, communicate via
if it's, they have some security stuff they talk about here. So I don't know because it's not even a product yet, but they say that they have some.
Startup.
Yeah, it's a startup that they're accepting pre-orders now. They haven't shipped yet. You have a comment?
Yeah, here's a good question. Like, don't they have that magnetic tab, whatever that you charge your phone? Couldn't you easily just set that there and charge it?
Yeah, but if you're targeting people that forget their keys, it's like.
Right, I'm just saying, like, just because that way you wouldn't have to plug in anywhere. You just set it and you charge it.
But that's the thing. You don't ever plug this one in.
Right.
But you could. You're saying you could.
You wouldn't
Have
have
it
to
down
buy
and
it
rest
every
forever.
year.
Right.
You just set it and charge it.
No, I absolutely. But part of this is the company is probably doesn't want to sell you one tile for the rest of your life.
Trying to keep a revenue stream coming.
Yeah.
But I'm just thinking, like, there's a loop, maybe.
No, you could easily put a loop in there, and in fact, there's a lot of research now in what's called energy harvesting, which is ways of collecting energy from like motion and other sources, and then using it for communication. So you could do that here. I mean, on the purse is a great example. On the bike is a great example, and then it would just charge itself over time too.
Right.
But yeah, I mean, they want to sell you another one next year, another one the year after that. So yeah. Otherwise, you'd move it around, and so I don't know. It's just something cool that I saw that it's kind of neat.
One more question on that,
Yes.
Professor. I guess in that portion where they showed the bike being stolen,
Yeah.
how they mentioned that the tile would network to anyone nearby who had the tile app on their phone
Yeah.
via Bluetooth. Does that not introduce a massive array of security concerns if you could, for example, spoof the protocol of a tile and then immediately be able to jump into anyone
Yeah.
else's nearby smartphone?
Yeah, one would hope that they did a good job on that, but yeah, that sounds like a source of, yeah.
Bluetooth is kind of notoriously a gray area for that security anyway. So.
Yeah, I mean, yeah, if it's using Bluetooth, we could build, you can actually build a Bluetooth receiver, like using the hardware in the lab, for example, and collect those signals. And yeah, I mean, I suspect it would be pretty easy to build a locator so that you could actually locate, because you could locate Bluetooth sources, so we could probably build that, and then I wonder if there's a special kind of a signature that these tiles have. So it's probably possible, but yeah, we shouldn't discuss that on this recorded World Wide Web. We could discuss that offline. It could be interesting. Yeah, another interesting source of business opportunity.
Consulting opportunity.
Or
right
yeah.
there.
Okay, so let's get back to the system at hand here, which is communication system. There we go. Okay, so part 2 here. Let me just get my 10:30. Trying to find the stop time here. Okay. So communication systems are band limited. So, and this forms the fundamental connection between communications and DSP here. So let me find the, shoot, I lost my numbering here. Let's see, 5. Here we go. All right. 7. Okay, yeah. So this is short. This is basically just an observation that communication signals are, and this is effectively, because we know that no real signal is band limited, but they are effectively band limited. And this comes about from essentially the transmitted signal being band limited. And because the transmitted signal is band limited, that means that the receiver only has to look in the band where the transmit signal is supposed to be. So the received signal can be treated as being band limited. And the implications of this observation is that, one, is that we're going to use Nyquist's sampling theorem, which we're going to go over next, to represent band-limited continuous time signals in discrete time. So we're going to represent communication signals in discrete time. This is great because now we inherit all the advantages of discrete time signal processing, and we can use those for communications. And that's all going to come through the sampling theorem. And then, as a byproduct of this, we're also going to model the channel in discrete time. And we'll see this at the end of the next lecture. But essentially, we'll be able to talk about generating a band-limited signal. We can do all of it in discrete time. And then, as far as processing goes, we can process our received signal all in discrete time. And then, to recover the transmitted signal from the received signal, we'll develop a discrete time model for the propagation effects, and then develop algorithms to remove those effects here. And so this is really, the fundamental connection between DSP and COM is from this band-limited property. So again, the implication of this is that the connection is fundamental. It's not that we're going to approximate, this signal with a discrete time signal. It's that it is exactly connected together. Okay, any question on this? All right, so we'll now see and talk about how to exploit this using the sampling theorem. So let's see, theorem. So this is the final part of the lecture here. So sampling. So I want you to be able to determine the sampling frequency for a given signal, the Nyquist rate, explain the theory behind sampling and reconstruction, and demonstrate aliasing. So all of these here are important. So let's continue now. So first of all, just the Nyquist sampling theorem using my notation. So the Nyquist sampling theorem states that something as follows here. So suppose that x sub c of t is a band-limited signal. For the next couple of lectures, I'll try to put this little c subscript to indicate that we're dealing with something that's continuous time. Later on, we won't need it because we'll be working primarily in discrete time. So it's a band-limited signal with Nyquist frequency of f of n. And what this means is that xc of f is equal to 0 for f greater than that Nyquist frequency here, f of n. And remember that there's always some tricky things that happen when you're talking about the frequencies right at the cutoff. So we call f of n here the Nyquist frequency. That's the highest frequency that's in the signal. So then, if t is chosen such that the sampling frequency f of s, which is 1 over t, is greater than 2fn, then x sub c of t is uniquely determined from its samples x sub c of n t. So periodically taking one sample from this signal every t tells you everything there is to know about x sub c of t here. And so some notation here, I'm going to call f of n here the Nyquist frequency, and fs here, sorry, let me see here. I should say that slight difference in notation here. So this is an f of n is the Nyquist frequency, and 2f of n is the Nyquist rate. So you can sample at a frequency greater than that. So the maximum frequency is the Nyquist frequency, twice the maximum frequency is the Nyquist rate. And there's always some debate about this because, you know, there's the terminology does vary in different places, but this is a pretty consistent terminology. And so it's what I'm going to use in the class. And so in homeworks and exams, you know, pay attention to if I'm asking for Nyquist frequency or Nyquist rate or both. So this is part of the sampling theorem. And then further, what this tells us is that we can write xc of t as a linear combination of those periodically obtained samples, x of n, which is just xc of nt, multiplied by a sine of pi t minus n capital T over t, divided by pi t minus n capital T over t. So let's parse this for a second here. So essentially, what this is saying is that we can rebuild the continuous time signal xc of t by taking, this is a shifted sinc function, and we're going to weight it by x of n and add it together. And so the typical picture looks something like this here. You've got, you know, a sinc function times x of 0, and then we have another sinc function here. Multiplying x of 1, etc., and you put them all together and you get some sort of a smooth signal where the values at these different points of t correspond to x of t, x of 2t, etc. here. So this right here, this formula here, this is called the reconstruction formula. So the sampling formula would just be x of n is equal to xc of nt. That would be sampling, and then this would be reconstruction down here. And so in this case here, at least in the time domain, the sampling is very easy, and the reconstruction is hard, because the reconstruction involves doing the sum over all these shifted sinc functions. And the sampling is just kind of like taking one out of every one of these samples every t here. All right, now we will also need to understand these connections in the frequency domain. So let's go now to frequency here. So in the frequency domain, this is in discrete time, x of e to the j 2 pi f, which is the Fourier transform of our sampled sequence x of n, is equal to 1 over t sum over n x sub c of f over t minus n over t. And that's the continuous Fourier transform of xc of t here. So this is this property in the frequency domain. Now, one thing that, let's just look at this for a second here. So there's a few aspects that are important. The first of all is the 1 over t here. 1 over t amounts to essentially like a conservation of energy. So if you didn't have this 1 over t here, kind of like the more samples you took, somehow the more energy there would be collected. And that's not really, that's just sort of an artifact of the sampling. So this 1 over t kind of takes that away. The second is that, look at this f here. This f is sitting on top of t, and that's kind of weird. But if you remember, f is basically unitless because it's going from 0 to 1 or minus 1/2 to 1/2. So this is multiplying the 1 over t, which is a fundamental frequency, or f of n. So actually this times this 1 over t is what's giving you hertz. And then this is an integer multiple of that 1 over t. And this whole thing is in hertz because that's a continuous time function here. So that's why it kind of makes sense here. The 1 over t is this kind of conservation, and then the 1 over t here is making all the units work out correctly. So any questions about that? Okay, now, one thing to note here is that, so if 1 over t is greater than 2fn, then x e to the j 2 pi f is equal to 1 over t x sub c f over t, for f in whatever range you're looking at. Let's say minus 1/2 to 1/2, or 0 to 1, whatever you like. So what this means is that if Nyquist has been satisfied, your discrete time Fourier transform, all it is a scaled version of your continuous time transform. Right? And that makes a lot of sense because we were saying that if we sampled correctly, this whole thing should be lossless. There's no information lost in the process. And so basically this is just a transformation from one to the other. Now, if that's not the case, then otherwise you get aliasing. And so the aliasing is caused by the sums of all these different replicas here coming in. Okay, so now I will just illustrate the aliasing concept. Again, something that is probably familiar, but it is worthwhile, to go through it again. Might be a while since you've seen it here. So let's just illustrate aliasing. And this is one of the things that I expect you to do. So either you know how to do it, or you will refresh yourself on learning how to do it for this class. So the way we typically illustrate aliasing is in the frequency domain, because drawing in the time domain by hand, these sinc functions would be really tough. We usually do this in the frequency domain. And I'm going to do this using the classic triangle function. Let's call this f of n here. This is going to be a 1. This is the absolute value of x sub c of f here. So this is my continuous time signal. I'll say this, some of you have heard this joke twice already because you've taken 2 of my classes before, but this is not the continuous time Fourier transform of any particular signal. This is just an example here, okay? So if you have like an exam problem and I give you a function and ask you to illustrate aliasing and you give me the triangle, I'm going to be very unhappy. So this is just an example. Yes, you know how unhappy I'd be, right? Just an example. Do not repeat this to show that, well, you didn't remember it, but you remembered the lecture or something or the other, don't do that. So that's the x sub c of f here. Now, let's look at two cases, one where we don't have aliasing and one where we do have aliasing. So this is going to be x e to the j 2 pi f, absolute value, where fs is greater than 2fn. So we have satisfied Nyquist. So the main things that we're going for here is we're going to rescale this. And since I'm just drawing this out, I can just change the label here. That's going to become 1 over t. And this value right here, remember now that this new discrete time frequency is going to be unitless here, so it should be somewhere between 0 and 1/2. So it's going to be like 1/2 here. And this value itself is going to be f of n times t. So this is what I find when drawing these out, is the most critical thing to find is this value here. So if you can find the fnt, then usually you can kind of sketch the rest of it by hand here. Right, and so then this here is going to be, and this is going to be a 1, because the replica happens here at 1, it's periodic with period 1. So this will be 1 minus fn of t. Okay, so that's what happens when there's aliasing. And this makes sense that we've got replicas because the discrete time Fourier transform has to be periodic. So we know it has to have replicas in there. And because we satisfied Nyquist, there's a big gap here and there's no distortion. But now we look at the classic example of the case where Nyquist is not satisfied. So let's go over here. So this is x, again, e to the j 2 pi f, magnitude here. So without Nyquist, we end up with, so the first thing to do is we draw out the triangle here. So the scaling factor is always the same, whether or not Nyquist is satisfied. That's not a big deal. The issue is the value of f of n t here. And so for example, let's see. I mean, we need an example to start with here. So if we take, suppose that we take t equal to 1 over f of n instead of 2f of n, then f of n times t would be equal to 1. So then we'd end up with something that looks like this here. This is kind of an extreme case, but when you'd add all these up, this would actually end up being a flat line. And I'll give you one more here. So if t is equal to, let's say, suppose that t is between 1 over f of n and 1 over 2f of n. Then you would end up with something where, I should just redraw it here on top of that. So you have your triangle function here, and then you would have some smaller amount of overlap. This is still f of n t, this is still 1, this is still 1 minus f n t, and then you'd end up with a signal that was looking more like etc. here. Now, things to note here is that you see this piece of the signal right here. This piece is actually undistorted, but there is aliasing over here. So I want to tell you that aliasing, not everything is lost, because you can still recover some piece of your original signal, but you don't get the whole thing. Nyquist doesn't give us the whole thing, but it just happens that we could still possibly get something here. And this fact is used in a lot of the constructions of practical analog to digital converters, because you can oversample and you can play other kinds of tricks where even though there's aliasing, you can get around it. So that's the aliasing concept here. And that's what I wanted to illustrate now. All right, so any questions about this here? Let's see where I am on the lecture 4. Okay. All right, the other thing I want to do is introduce some graphical notation here. So the graphical notation that we'll use to illustrate sampling and reconstruction, this comes from the Oppenheim-Schaefer book. So I'll use this block diagram that looks like this here. So it's going to be what's called a discrete to continuous converter operating at some sample rate t, producing x of n here. So this D to C is discrete to continuous, and this is the sample period down here. And all this device is doing is just creating this here. But so in a lot of our block diagrams, when we want to do sampling, we'll put in this D to C here. Now, why we're using a D to C and not a digital to analog converter is as follows here. So this is essentially just an ideal digital to analog converter. So a real digital to analog converter, first of all, takes a digital input. It doesn't do the reconstruction operation perfectly. So it's not exactly ideal. So it's got, that would be D to A, and there's various other sundry imperfections associated with it. So for the class, we are going to use the D to C notation here. And in the lab, the way we're operating the digital to analog converters is we have pretty high resolution, and we're not operating them at their limits. And so they behave close enough to a discrete to continuous converter. But if you wanted to, if you are working with a team of systems engineers, you might actually work with them to modify, the digital processing based on the fact that these things might not be ideal. Any comments on that? Questions?
So you're
Yep.
putting in this continuous signal,
Yep.
and you're getting out discrete signal?
Yep. Yeah, so sort of a weird block. If we were going to characterize this from a signals and systems perspective, it's not really like a time varying. It's a time varying system, because if you shift the input signal, the output totally changes. It doesn't shift. And then linearity is satisfied. But yeah, it's a weird kind of a system block. So continuous comes in, discrete comes out. And it's just
Isn't it continuous to discrete?
yes, continuous. Sorry, did I write this wrong here?
Discrete.
Right, yeah. What am I writing here? Shoot. Yeah, that makes absolutely no sense. Yeah. Start this again. Okay, sampling notation. So the sampling notation is what we're going to use to illustrate sampling and reconstruction in a graphical form. So first we'll start with the continuous to discrete conversion. So I take x sub c of t, goes into some c to d operating at sample period t to produce at the output x of n, which is equal to xc of nt. So c to d is equal to continuous to discrete and it's an ideal analog to digital converter. And it's ideal because we're not considering all the analog imperfections associated with an A to D, like the slew rate. We're not considering the quantization effects that also happen in analog to digital converter. So we're assuming that essentially that the analog to digital converter is very well behaved and has infinite resolution. And so that's the sampler, and then the reconstruction would be equivalent of this here would be x of n going into a d to c with input t, producing at the output x sub c of t, sum over n, x of n, sine of pi t minus nt over t, divided by pi t minus nt over t. And so that's the reconstruction. And then this is just essentially an ideal digital to analog converter. And so again, we don't have, the quantization effects. A lot of times also digital to analog converters, they don't do a very good job of implementing the sync function. They might just have like a rectangle, for example. And so then you need subsequent filtering to fix that up. Or you could do it digitally. So, but anyways, for the development in the class and also in the labs, it's sufficient to use essentially the ideal forms of those converters. So any questions about that? I think I got it correct this time. Okay, so that's actually it for lecture number 2. Sorry, lecture number 4. So this was lecture 4 here. Let me take up the sheets here.
So should we break these up?
Yes, I'm going to stop for about 5 minutes, and then we'll restart.